So the Daniel Green will talk about the status of inflation. Please.
Okay, well, thank you so much for the invitation, and thanks for accommodating me remotely. I'm sorry I couldn't be there. So my plan for the talk is that first I'm going to give some just general motivation for why we're continuing to explore inflation and what kind of things we're hoping to learn. Then I'll talk about the status of single field inflation. We'll talk a little bit about multi-field inflation. And then we'll move on to just cover a few of the recent theoretical developments, maybe focusing on things I found particularly interesting, and then conclude talking about the sort of landscape of observations kind of in the next decade or so. Okay, so if you've been to a talk on inflation, you've probably heard the same story. It's always told in the same way. There's a story about how the universe started, or before the hot Big Bang, there was a period of exponential expansion that we call inflation. And this story usually tells us that the exponential expansion is driven by a fundamental scalar field rolling on a potential of a shape something like this. So the idea is that the equations of motion for this scalar field obey the same equations as a ball rolling on a hill. And when the ball is at the top of the hill, its energy is dominated by potential energy, which is constant while the ball is up there. This looks like a positive cosmological constant, which drives the exponential expansion that's needed for inflation. Now, because this is a quantum field, it has quantum fluctuations, and these quantum fluctuations of our fundamental scalar are supposed to be responsible for the initial density fluctuations that seed structure in the universe. Now, we've observed density fluctuations over several decades in scale, and the picture that we're usually told is consistent with those observations. So we see approximately scale invariant spectrum over sort of 2 orders of magnitude, and that points to the same kind of physics that would be of a ball rolling on a very flat potential. However, not everything that looks scale invariant has to come from simple dynamics. And there are many examples in nature of scale invariant phenomena that owe scale invariance to much more complex dynamics than just these simple ones I've described so far. So the question we want to ask is this necessary? So with this in mind, over the past 10 years, the community has sort of described inflation in a more general setup in order to better ask this question. So the inflation in the modern language is really 2 conditions. The first condition is this period of exponential expansion. So we think the rulers in the universe are described by a scale factor A of t that grows approximately exponentially in time, where the expansion rate, the Hubble parameter during inflation, is nearly constant. So the time derivative of h is much smaller than h squared. Now, this is defined to be a period of inflation, so it doesn't last forever, which means there exists a time in the universe when inflation ended. In general relativity, the use of the word time requires a physical clock to measure it. So if you're going to say there's a time when something happened, the universe had to be filled with some sort of physical clock that defines what you mean by that time. In slow roll inflation, the scalar field is the thing playing the role of the clock. So the scalar field evolves almost linearly in time, which means that if I had like a little detector that measured the local value of phi, I could set my watch to the value of the background scalar field. Now, this raises the obvious question of what is the clock? We make clocks in the real world. They're not made of fundamental scalar fields. They're made up of things that evolve in some dynamical way. Relatedly, we have lots of models of inflation, some of which have very complicated dynamics and do many different things in our simple picture. And they also typically give the same kinds of scale invariant power spectra and similar predictions that are consistent with data. So in general, we want a way to organize our observations that we can test this framework. Now, for the purpose of the talk, a lot of what I'm going to focus on is primordial non-Gaussianity. Non-Gaussianity is a useful way of testing the nature of inflation because it's kind of what's seen in examples as a residue of doing more dynamical models of inflation. This could be because we've created a model with strong self-interactions rather than the flat potential, or because we've introduced couplings to other particles to slow down the scalar field on a potential, or just as a way of understanding nonlinear dynamics more generally. All of these ideas tend to show up as changes to the statistics. Okay, so with that in mind, we're just going to quickly review what I mean by non-Gaussian statistics, again, because that theme is going to come up through the talk. So in cosmology, we're used to talking about the CMB, for example. In this case, the Gaussian statistics mean we're just measuring 2-point correlations of temperature. So that means I look at the temperature in one part of the sky, I look at the temperature in another part of the sky, and I average over all possible temperatures that are separated by the same distance, and that gives me a correlation function of temperatures. This is directly related to the 2-point function of the initial density fluctuations, which we'll typically call zeta. I'll explain that later on. However, because the universe has underlying homogeneity and isotropy, this function is pretty limited. It has very limited information about the model of inflation. It usually just tells us if it's scale invariant, it's completely fixed. So all we really measure is a deviation from scale invariance with the 2-point function. On the other hand, the 3-point function, taking 3 temperatures and averaging over the sky, has a lot more dynamical information. And this is true not just in the CMB, but you can think of this in any cosmological map. I can take any map of the universe and talk about taking 3 points and how they're averaged over space. Now, on general grounds, because of the sort of flatness of the universe, the flat slicing of the cosmological universe, we know that if I take 3 fluctuations and I take their Fourier transform, their correlation function is some overall function of the length of those 3 Fourier modes. And those 3 Fourier modes must form a closed triangle. This is momentum conservation, if you like, or it's just translation invariance. So this tells us that the dynamical information is encoded in the shapes of triangles. Now, there is the overall scale of the triangle, but if I additionally assume that the physics of inflation is scale invariant, then I'm really just reduced to cross ratios, the shape of the triangle where I fix one side to be length 1, for example. Now, in cosmologist terminology, we usually take this 3-point function called this Fourier transform of the 3-point function called the bispectrum and decompose it into an overall amplitude whose name is usually F and L, and a shape function that is often called S. This shape function is a function only of these cross ratios and has a really interesting property, which is that it defines a basis of orthogonal functions on the space of possible 3-point functions. So specifically, if I define an inner product between 2 possible shape functions by just integrating over these cross ratios, then when this inner product is small, it means I can measure those 2 shapes simultaneously without much correlation. On the other hand, when this inner product is close to 1, then it means that the 2 shapes are very hard to distinguish with data. So this shape function is very useful because using this inner product, it allows us to go between theory and data very easily. Now, the one thing that's not so useful about this definition is that this parameter F and L is normalized in a funny way. It's normalized such that roughly the amplitude of fluctuations, 10 to the minus 4 times F and L, is of order 1 when the statistics are pretty non-Gaussian. So said differently, you should compare the number F and L to 10 to the 4 and not to 1 as a measure of Gaussianity. So said differently, if I add some interaction to my theory that's suppressed by a scale lambda, then weak coupling means that Hubble over lambda is much less than 1, and that will correspond to F and L times delta much less than 1, or F and L much less than 10 to the minus 4. Now, cosmologists often then focus on 3 particular shapes. They tend to characterize a lot of the useful information. There's the local shape, which I'll explain where it comes from later in the talk. It's peaked in configurations where one of the sides of the triangle has been collapsed. sometimes called the squeeze configuration because I'm squeezing one of the sides of the triangle. The next shape has a more obvious name. It's called the equilateral shape. The shape function is peaked in configurations where the triangles are equilateral or all three sides are the same length. The final shape, called the orthogonal shape, has contributions in both equilateral and flattened triangles, but it's defined so that the inner product between the orthogonal shape and the equilateral shape is 0, hence the name orthogonal. It's defined purely by its inner product. Okay, so that's the context for most inflation, a lot of the probes of inflation we're going to talk about in this talk. Okay, so now on to inflation itself, single field inflation. So the definition I used before, where there are two conditions for defining inflation, especially the second condition, the presence of a physical clock, are formalized in the EFT of inflation in the language of particle physics. So specifically, the presence of a physical clock tells us that there's some operator who requires a vacuum expectation value that's proportional to time. Hence, if I go and measure that operator, I can measure time anywhere on a space-like surface. Now, again, in the language of particle physics, we've spontaneously broken the time translations of flat space, and therefore I should introduce the Goldstone boson associated with that symmetry breaking. And I do so in the following way. So I introduce the Goldstone boson so that some variable u transforms like a scalar under time translations. Now, the need for this Goldstone boson is the same reason that there's no such thing as a perfect clock in a quantum mechanical world. So this pi is really the fluctuations of my clock that have to be there because I can't possibly measure time with perfect accuracy. Now, the usefulness of defining this variable u is that because it transforms as a scalar, I can define the most general possible action that characterizes this phase of the universe as a general function of u and covariant derivatives. This ensures that anything I write down has its origin in a Lorentz invariant theory, and it's only the vacuum expectation value of these operators that's generating the non-Lorentz invariant looking terms. Now, in reality, we live in a world with dynamical gravity. Time translations are gauged. And so ultimately, gravity is going to eat the Goldstone boson so that it lives inside of the metric. So this is the variable zeta, the scalar metric fluctuation, or the adiabatic fluctuation. And in the relationship between this adiabatic fluctuation and my Goldstone boson is typically given by just a constant, minus h, up to terms that are typically negligible. In fact, this precise relationship can be formalized by using a version of the Goldstone boson equivalence theorem that says if I decouple gravity by taking m Planck to infinity and h dot to 0, holding this product fixed, I'm left only with the action of my Goldstone boson completely decoupled from gravity. In practice, what this means is that for the purpose of studying the dynamics of inflation, we can usually just focus on the Goldstone boson action and ignore the consequences of coupling to gravity. So this effective field theory is characterized by energy scales. So at the highest energy scale, there's gravity, set by m Planck. As we come down in energy, the first scale we hit is the decay constant of a Goldstone boson, f pi squared, which characterizes the scale at which time translation symmetries are broken. So in slow roll inflation, this f pi, which you can define in a model independent way, is equal to phi dot, which is the scale characteristic of the breaking of symmetries. So this is the scale where both time translations and boosts are broken. Now, as we go down in scale, we eventually hit Hubble. This is the scale at which particles are produced from the vacuum because of the expansion of the universe. If you go down further still, you hit the scale h dot. This is the scale where the background deviates from being de Sitter-like, and you pick up this slight time variation of the background. Now, what we know about these scales from observations is that the ratio of the pion decay constant to Hubble is what sets the amplitude of scalar fluctuations. So given that we've measured the amplitude of scalar fluctuations, we can infer this ratio of scales. Specifically, the pion decay constant is 59 times the Hubble scale during inflation. Now, we don't know Hubble, but we know the ratio. Okay, that's what we learned from the 2-point functions, as you would imagine, since the pi on decay constant is what multiplies the overall action. Now, we want to go on further and learn more about this sort of general object that describes the effective theory of inflation. So typically what we do is we just Taylor expand this function, keeping track of derivatives so that they form scalars under the Lorentz group. It's particularly useful, this is just a practical tool, to combine derivatives in such a way so that you cancel off the derivatives that all hit the time component. So for example, you often will see expressions of the form d mu u plus 1. The plus 1 is just there so that this term starts at order pi. In this description, then the leading order in derivatives per field, the action takes the following form. It's an expansion in d mu u plus 1 to the n with some overall constants so that the terms start at order pi to the n. Okay, this again is just for human convenience. There's no deep significance to this organization. Now, so with this organization, though, the action starts. We see that the action starts at quadratic order in terms of a single parameter. So there's a single quantity that, other than the decay constant, that determines the behavior of the model, which is the speed of propagation. So this speed of propagation, sometimes called the speed of sound, is what relates to time and space derivatives. Interestingly, this parameter also controls the leading interactions. So as we make the speed of sound smaller, we necessarily increase the size of the cubic interactions in our model. And therefore, there's a relationship between the speed of sound, which controls the propagation in the quadratic action, and the interactions, which controls non-Gaussianity. Now, because these are all derivative interactions, this is a Goldstone boson after all, so it has this underlying shift symmetries. These interactions come suppressed after canonically normalizing by some energy scale. The amplitude, therefore, of the 3-point functions, the non-Gaussian statistics that arise from this interaction, are there a ratio of the Hubble scale to the scale associated with this interaction. And this is what we're measuring when we put bounds on this equilateral shape. So this gives you equilateral non-Gaussianity, where the amplitude of the equilateral non-Gaussianity is controlled by this ratio of scales. Alternatively, one can take all of the non-Gaussian information and convert it to a bound on CS by marginalizing over these other parameters. And so sometimes you'll see the constraints on non-Gaussianity expressed as a lower bound on CS. But for us, it's more useful to talk about energy scales. So what we learn from this bound from Planck is that the scale, the strong coupling scale of our effective field theory, is above Hubble. So we've found that the fluctuations are pretty Gaussian. We see no deviation from Gaussianity. That tells us that the Goldstone boson is pretty weakly coupled. And that weak coupling is reflective of the fact that this energy scale is above Hubble. So it's about 5 to 10, depending on the specific operator you look at, times Hubble. Now it's important that even though this is above Hubble, it's still significantly below the pi on decay constant. And the reason that's important is that in slow roll models, like the ones we started with, this simple picture, these models have to have this decay constant above the strong coupling scale of the E of t above the decay constant. This is just saying that this scalar is weakly coupled. The dynamics are described by a free field with a potential, not by some very dynamical, strongly coupled system. That means that there's this huge range of scales, basically lambda between 5 or 10 and somewhere above 60, that are currently allowed by data, but would, if you were to find F and L in this region, would rule out this conventional picture. Okay, so that's the status so far of single field inflation. There's lots more one can say about single field inflation, but from here I'm just going to move next to multi-field inflation. Unless there are any questions so far. Okay, so moving on to multi-field inflation. Okay, so what makes Yep.
Can I ask a question?
Of course.
So you are talking about the cutoff scale from the interaction terms.
Yes, correct.
This all the stones. So you are putting a bound on this cutoff scale.
Correct.
Non-Gaussianity. But you are saying also the cutoff scale for single inflation, which is far beyond the symmetry breaking scale. So you are talking about two different scales.
Yeah, so this is unlike QCD. So so QCD would, let's say we're talking about pion physics. Pion physics of the real pions of QCD, the interactions are related to F pi, right? There's a strength of interaction that's controlled by the pion decay constant. But those come with only two derivatives, right? So the two derivative action is completely fixed by F pi. But these terms have higher derivatives. So you should think of them in QCD like higher derivative non-universal terms that are not fixed by the nonlinear sigma model. And so those come with their own scale. Now in QCD, you can prove by some rules, some bounds on those just from consistency. But here, we just don't know anything about them. So we're going and measuring those non-universal terms in our pion action. Does that help?
Okay, so still you are adding higher dimensional operators, which is consistent with the symmetry of the original Lagrangian at the two derivative levels, right?
Correct. So now I should also say, even though this picture looks unconventional, so you might worry, well, how did you get scales so far below the pion decay constant? There are plenty of models that produce this exact hierarchy of scales. So for example, dBi inflation produces this. And in particular, what happens at the scale of lambda is that the square root action of the square root dBi action can no longer be Taylor expanded. So if you try to Taylor expand dBi, it works perfectly fine at low energies, but around this background, the Taylor expansion breaks down at lambda, even though the pion decay constant is much higher up at F pi. Does that help?
Thank you.
Okay. Okay, so one of the things that makes multi-field inflation particularly exciting is that because of both the dynamics of the background geometry and the possibility of dynamics during inflation, you can imagine exciting particles of masses all the way up to the pion decay constant. So for sure, any particle whose mass is around the Hubble scale will be produced from the vacuum just from the expansion of the universe. But additionally, by coupling to the inflaton, because the inflaton itself breaks Lorentz invariance, you can violate energy conservation and produce particles all the way up to F pi from the vacuum at sort of an order 1 level. So this means that the space of multi-field inflation models is not just extra light fields, but really covers anything that has masses of the same order as the relevant scales for inflation, like Hubble, which in high-scale models can be up near the gut scale. So the simplest way we can consider this multi-field models is in the same way we would approach any EFT, is we would take our goldstones and start now just coupling them to additional sectors. So we have the rules for how to write down an action of just the goldstone, and of course by those same rules we can write down couplings to other fields. This kind of setup is typically called quasi-single field inflation, which is inspired by that name comes from the original model of this type that was considered by Chen and Wang in 2009. That model was the simplest possible setup where you have just a mixing interaction between the Goldstone boson and some second field we'll call sigma, but then you can turn on a big self-interaction of sigma. This operator would not be allowed if we were to write the similar operator for pi. So by mixing between sigma and pi and then turning on this term, we can generate new kinds of non-Gaussianity that wouldn't be allowed for the pion itself. When this parameter mu, which controls the strength of interaction, is order h, you get very large non-Gaussianity. In fact, it's large enough, depending on details, that it's already been, some of those operators cases have already been excluded. But you can take this idea and you can extend it. You can consider higher point functions, more complicated self-interactions. You can apply it sort of more model independently, and you can just think of what the role of this particle is doing, even in the case where the particle is actually very heavy. So that's quasi-single field. And the more conventional, in addition, if we have light fields, then we have to consider the possibility that those additional light fields survive to the end of inflation and dictate how reheating happens. In that case, you can have a non-trivial mixing between the metric fluctuation during inflation and what were isocurvature fluctuations during inflation, so that the actual adiabatic metric fluctuation that we observe is some combination of both these spectator fields or these other light fields and the metric fluctuations during inflation. These additional fields can also have interactions that generate their own non-Gaussianity during inflation, but if they're decoupled from the inflaton, these correlators are more constrained by symmetries because they look like they're living in de Sitter space with the full Lorentz symmetry. The simplest version of this kind of setup is what gives the local non-Gaussianity. So if we imagine that the only thing that matters at the end of inflation is a totally Gaussian field that becomes non-linearly related to the metric fluctuations, then you produce this local shape. The local template is precisely this model. In models that produce local non-Gaussianity, you usually produce FNLs of order 1 at least, and that's because any nonlinear process typically has a sort of Taylor expansion with order 1 coefficients. Now, in practice, you can sometimes fine-tune these coefficients to be much smaller, but that's just an interesting target of FNL local of around 1. Current constraints on FNL local are at the sort of 10 at 2 sigma level. Now, of course, local non-Gaussianity and equilateral non-Gaussianity live at opposite ends of a continuum that are controlled by the mass of particles that could be coupled to the inflaton. So if we have zero mass, then we still get these local non-Gaussian shapes. If we had very massive particles, we can integrate them out to produce equilateral non-Gaussianity. And in between, we get these sort of hybrid shapes, all of which have been searched for in the Planck data to produce this kind of constraint. However, I should emphasize that in reality, there's a possibility that the dynamics and the ending of inflation involve a much more complicated relationship between the inflaton and these additional fields. And there's actually a lot of phenomenology that has yet to be explored. So a lot of what's going on in the field, as I'm going to get to in the next section, is actually about trying to understand the space of multi-field models more generally, not just in the limit where it's perturbatively coupled to an inflaton. Okay, so that brings us to the next topic, which is recent developments. So the one you've maybe heard a lot about is the cosmological bootstrap. The cosmological bootstrap is a program of trying to derive the predictions for these non-Gaussian correlators directly from fundamental principles. So the idea is to circumvent the process of writing down a Lagrangian and directly write down the correlators based on principles, kind of what people do with scattering amplitudes. Now, the reason for that is rooted in the relationship between scattering amplitudes and cosmological correlators. Specifically, every cosmological correlator contains a scattering amplitude. So in a precise way, these correlators contain what's called a total energy pole. So what that means is that there's a term that looks like the sum of the lengths of the Fourier modes to some power. And if you analytically continue this quantity, the residue of the pole when this total energy vanishes is the associated scattering amplitude of n scalars when I have an n-point cosmological correlator. This kind of phenomena is interesting, and it's why this bootstrap program focuses on the analytic structure in this kind of complex energy plane. So roughly speaking, the idea is something like this. Correlators are encoded in some physical regions of momenta. So for example, for physical Fourier modes, the energies are always positive. But as we analytically continue them into the negative region, we find properties that are associated with scattering amplitudes, like we resolve the tree level amplitudes, or they obey factorization properties similar to what's known for computing exchange diagrams. In general, this motivates the exploration of the scattering amplitudes of the effective theory of inflation. So by taking this decoupling limit I talked about before, and then taking H all the way to 0, we're left with an effective theory for the Goldstone boson that lives in flat space. By studying those amplitudes, so by directly studying the amplitudes in that theory, you can then bootstrap the correlator that they correspond to. So this is particularly work being done by Enrico Payer and his group in Cambridge. Like other effective field theories in flat space, the soft behavior of these amplitudes kind of is encoding the structure of the EFT of inflation directly in the amplitude. The other obvious thing you'd want to do, given what has been interesting direction of research, is to put positivity bounds on the couplings of the EFT of inflation by considering scattering amplitudes. This is more difficult in this context because the scattering amplitudes do not obey Lorentz invariance. Now, one limitation of the cosmological bootstrap program so far is that it's been mostly perturbative, and in most cases actually focused on tree level correlators and amplitudes. There's been some work at loops and some also progress in trying to define the entire bootstrap program non-perturbatively, hopefully in closer connection to the conformal bootstrap. Now, speaking of loops, another direction of research has been the understanding of loops in de Sitter space and in inflation. This has long been the source of confusion, specifically around the topic of IR issues. The origin of this problem starts even without gravity. There are divergences. There are IR divergences in loop momenta, which are confusing. There's also secular growth. This means that there are correlators that you calculate perturbatively whose answer grows with time so that the answer diverges as t goes to infinity. The origin of these problems of the confusion tends to be that typical regulators like dimensional regularization don't work very well, and so it's hard to actually regulate diagrams in cosmological backgrounds or calculations and loop calculations in cosmological backgrounds. And in addition, because you have a function of time, it's hard to know how to do power counting, because depending on the time at which you evaluate something, the effect could be either big or small. There's kind of not a natural order parameter. Now, recent work has really understood a lot of these issues, particularly in pure de Sitter space. So a lot of what was confusing people before can be traced just to the lack of good regulators. So there are a lot of divergences that are better understood as just standard renormalization. The exception to that is light scalar fields. So in the limit of zero mass, scalar fields really do have some unusual properties that are not so easy to see as being related to field theory. But what we've understood now is that those IR issues are really signaling the need for a non-trivial renormalization group flow associated with those light scalars. So when you understand that renormalization group flow, you can take all of the Kalin-Zemansky equations for the operators in the theory and rewrite it as a single master equation for the probability distribution of the scalar fluctuations. And at leading order, that equation for this master equation for all those Kalin-Zemansky equations is the framework known as stochastic inflation. It's this Fokker-Planck equation for the probability distribution. Now, this equation, as written, is in one-to-one correspondence to operator mixing, so you can calculate this just by calculating what you'd consider anomalous dimensions. Now, the physics is this old picture where we have a scalar field on a potential. There are quantum fluctuations that produce noise. That's the first term. And then, of course, because it's on a potential, it has classical drift, which drives it to the bottom. And that's the second term. Now, if you can solve this equation to find the late time behavior, and it obeys some probability distribution where you essentially fill up the potential to height h, and then it falls off after that. Now, the boundaries of this equilibrium distribution go like 1 or over the fourth root of the coupling. So as you take the coupling to 0, the field range goes to infinity. Now, this might cause you some concern, and so a natural question is whether those large field ranges are under perturbative control. 1 over couplings seem dangerous, and you want to understand them. So the way to think about this is just to start by thinking of the most general possible corrections to this framework. So we could imagine some totally general Markovian process where this probability distribution evolves in time according to transition amplitudes, which we can interpret just as the probability of hopping into a certain point or hopping out of the point. So specifically, the change in the probability distribution is just the amplitude of phi leaving where you are, and the probability of jumping into the point minus the probability of jumping out of it. Now, if we assume that this Markovian evolution is dominated by small jumps, then we can just Taylor expand in the jump size and rewrite this as an expansion in derivatives multiplied by field-dependent moments that capture the transition amplitudes. In this way, we see that all of that information is encoded just in corrections to this derivative expansion. And in particular, more than two derivatives corresponds to non-Gaussian moments of the transition amplitudes. So if we just take the ansatz, we take this ansatz and apply it to this scalar field in de Sitter, we would expect there's a very large number of corrections, including higher powers of phi and higher powers of derivatives. But if we take an educated guess that we're supposed to count powers of phi like 1 over square root of lambda, but we're supposed to count these corrections like linear powers of momenta to the appropriate power, then we get a well-defined power counting, where at leading order, it is just the old Starobinsky stochastic inflation that controls the evolution, and then there are corrections at higher powers of lambda next to leading order and next to leading order. The most interesting of these corrections arises at next to leading order, where it's the first appearance of non-Gaussian noise associated with this cubic term. These corrections have been calculated, so next to leading order, you can find the coefficient of non-Gaussian noise. In addition, you can find there's an effective potential, and in fact, this effective potential can be calculated to all orders, but here's just the next to leading order corrections. You can then take this equation and calculate whatever you want at this order, corrections to the equilibrium distribution, corrections to the relaxation eigenvalues of the equations. Now, one of the things that we thought to do with this framework is to try to use it to calculate the tail of the probability distribution. This is particularly interesting in models where the information seems to live at the highest endpoint functions. So they're typically the lowest endpoint functions, like the 2 and 3 point function, have most of the cosmological information. But in some situations, it seems that it's the very high endpoint functions that have most of the information. There's a relationship precisely between situations where the endpoint functions are important and situations where the tail of the probability distribution are important. What's interesting is that when you try to calculate the tail of the distribution, you find a breakdown in effective field theory. So specifically what happens is when you go out on the tail, you're exploring higher energy processes. So if you go too far on the tail, then eventually you're looking at energies first above the strong coupling scale, eventually up above the pion decay constant, and if you go far enough, you'll be even sensitive to Planckian energies. This entire process can be understood as an example of something that's well known in the math literature as the large deviation principle. And so this is an interesting area of exploration where the tail of the distribution really depends on the microphysics of the model and can't be understood just in terms of effective field theory. Okay, so hopefully that's a nice sample of some interesting theoretical developments. I'm just going to end with some directions for future observations, but I'll pause here for the questions about the theory side.
I'm sorry, can I ask a question?
Of course.
Yeah, I don't know if I could understand correctly, but you say in the multi-field inflation, we have local type non-rationality, and maybe for the equilateral type, maybe can be obtained, maybe is for typical for the single field inflation. First, is it roughly correct understanding?
Sorry, can you repeat? You said large field inflation and local non-Gaussianity. I'm trying to understand your.
I understand you mentioned for the large field inflation, we get local type non-Gaussianity typically.
Oh, so no, so my comment in large field, okay, so for large field inflation, which is high scale inflation, the problem that the scales are very high, and so it seems likely that there are new particles. And therefore, it seems unlikely that you could completely ignore the presence of these new particles. Now, that may not be local type, but these sort of quasi-single field type non-Gaussianity, that it's somewhere in the middle. So I would say that for large field, one might anticipate this kind of non-Gaussianity that sort of lives in the middle of this diagram. However, to create models that have large field range is challenging, and that might mean that you have to decouple the inflaton from these extra particles. So it might be that large field models, in order for them to work, can't have this kind of non-Gaussianity. But again, this is a much broader model building question that I don't think we have the real answers to.
Yeah, so my question is, what is, when the orthogonal type is, how to say, important?
The oscillon, is that what you're asking? Or just mean oscillatory shapes?
Yeah, orthogonal shape, yeah.
Oh, sorry, the orthogonal shape. So orthogonal shape typically arises in the same context as equilateral. So equilateral and orthogonal basically arise, and they're just at the same time. And let's see if I don't have to go back too many slides. You can think of the reason why that they have those two shapes as just a tool for measuring the two independent coupling constants. So there's one coupling constant at 3 points that involves CS, and another coupling constant involves a different parameter. And so orthogonal is really just invented as a way to split these two operators. That's what gives you this space, is by measuring orthogonal and measuring equilateral. But physically, it's really the same mechanism. It's just derivative interactions. Does that make sense?
Yeah, okay, thank you.
Any other questions?
I think there are no more questions.
Okay, I'm going to move on, hopefully not to go too far over time. Sorry for scrolling so fast. Okay, so state of observations going forward. So the first and most obvious probe of inflation that's ongoing is the measurement of primordial gravitational waves. Gravitational waves just see the de Sitter background. They don't really couple to inflation unless you work hard to do so. And so their amplitude is usually completely determined by the ratio of Hubble to the Planck scale. And since we measure the Planck scale, that's just a direct measurement of Hubble, the scale of inflation. This program of searching for gravitational waves focuses on the B-mode polarization signal in the CMB. The sort of best constraints so far have been coming from the South Pole, particularly from BICEP, and in the future with help from SBT, also located on the South Pole. There is ongoing work as well from ACT and Polar Bear in Chile. Moving forward, the plan has been to really focus the effort in the South Pole, basically SBT and Keck eventually turning into a number of B-mode focused telescopes in the South Pole that would produce these kinds of figures that you've seen in the science book for CMBS4. This is still not entirely certain. There will definitely be a program of observing the CMB from Chile, particularly just for the usual CMB science, both from the Simons Observatory and eventually CMBS4. It's less clear if this will also involve B modes. That's still up in the air. Now, one thing we already know is that the future of understanding inflation is not going to be entirely dominated by the CMB the way it has been so far. The reason is that there's just not enough information left in the CMB to push our information about inflation where we want it to go. So specifically, we've measured most of the modes in temperature and E-mode polarization to around L's of 1,000. CMBS4 can get out to L's of 3,000 or 4,000. Maybe a little over 4 for E-modes. The problem is that the scaling of the constraints on non-Gaussianity with the highest L of your data isn't very favorable. So even a factor of 4 only turns into about a factor of 2 in constraining power. So if you look at CMB stage 4 forecasts for FNL equilateral, FNL orthogonal, they're basically a factor of 2 better than where we are with Planck. Part of the reason for this weakness is because of the projection from 3D to 2D. So you'd have expected maybe a factor of 4 just from mode counting, but because you have to take a 3-dimensional triangle configurations and project them onto the CMB sky, that's what gives you this extra square root. The ultimate plan for where to get more information is to go to the large-scale structure of the universe. This is the 3-dimensional volume between us and the cosmic microwave background. The basic reason is just there's more information there. The number of modes in the CMB we can measure is basically set by the number of pixels of the CMB sky, which is the ratio of the smallest scale to the largest scale squared. This large-scale structure is 3-dimensional. So even if you were to measure the same scales, you would have to cube that in order to get the number of modes available. In addition, we may potentially be able to go to even smaller distance scales than we can in the CMB, leaving the opportunity for vastly more information on large-scale structure. Of course, with great power comes great challenges. The low redshift universe is much more nonlinear than the CMB, and extracting cosmological information is much more challenging. Even in dark matter only simulations, we see lots of complex structures that are hard to understand in perturbation theory, or to model accurately in perturbation theory, I should say. And then you have the whole problem of adding realistic physics, baryons, the formation of actual galaxies, star formation, feedback from AGNs. This is a very complicated problem, and realistically, we're not going to be able to solve this entirely with computers. So the strategies that have been employed are kind of threefold. There's inflationary model building. So here the idea is like, maybe our model of inflation has a really interesting signal that we can pull out of the mess of large-scale structure data. The second strategy is just pure modeling. So here we say, look, we're going to do simulations, we're going to add the baryons, we'll do machine learning to speed it up, and maybe we'll incorporate ideas from effective field theory or perturbation theory as well. The last approach is principles. So the cosmological data is still governed by the same principles as the rest of physics: locality, causality, symmetries. And we can try to use that information to define protected observables, observables where the nonlinearity can't change the answer, even if we don't fully understand. So just as a highlight of some of the examples of these different approaches, so first there's just the model building approach. So axion monodromy is a nice model that comes from UV physics. And the idea of axion monodromy is that the inflaton is some kind of axion associated with a winding direction of some compact direction. But because of monodromy, it generates a potential that doesn't look like an axion potential. But because of so it winds around this direction many, many times, but as a result, the usual cosine periodic potential is still there. This produces wiggles in the power spectrum. And these wiggles, we can show, never are produced by nonlinear physics. The wiggles survive any nonlinearity because you don't generate this from just local processes. Using this idea, you can actually already produce better constraints using BOSS data from large-scale structure than you can with the CMB. So here's an example of limits on the amplitude of primordial features, comparing BOSS-only constraints in red to Planck constraints over the same range of parameters, and you see a factor of 2 to 4 improvement. Looking forward, this will improve, large-scale structure will improve constraints and primordial features by up to a factor of 100, and will already with DESI, which is taking data, exceed even a cosmic variance limited CMB experiment. So better than the best possible CMB measurements. Okay, next strategy is principles. So this is highlighted by quasi-single field inflation. In quasi-single field inflation, you produce these 3-point functions that owe their origin to some second lightish field. These extra fields violate a set of principles known as the single field consistency conditions, which are basically a way of encoding the equivalence principle. Now, this violation of the single field consistency, the consistency conditions can be taken all the way through to large scale structure. And it shows up as a relationship between as a non-local relationship between the galaxies and the matter. So roughly speaking, the density of galaxies doesn't trace the matter, but traces something like 1 over Laplacian to some fractional power of the matter. This is something you would never get from local physics. It's a complete violation of the equivalence principle, and is a relic of the fact that there was a second field that was required to produce this signal. This is looking for this non-local signal is the strategy of the Sphere X experiment and all the local tests of local non-Gaussianity in the next generation, and they're expected to produce a factor of 10 improvement in the constraint of local non-Gaussianity. Okay, but so to conclude, we're going to come back to our sort of favorite threshold, equilateral non-Gaussianity, trying to rule out all of this region that is inconsistent with the slow roll inflation picture, but consistent with Planck. Now, here the problem is most acute. You just have triangles that look a lot like triangles that are produced by nonlinearity. So the strategy that's been taken so far is just modeling. The hope that we're going to model the nonlinear signal sufficiently accurately that we can separate out the primordial signal. Now, the modeling process is very complicated. We start with the initial conditions from inflation. Then we have nonlinear evolution to dark matter. Then we have creation of dark matter halos. Then we have formation of galaxies, all the way through the redshift space distortions and the description in terms of data in terms of angles and redshifts. Typically, this procedure requires cutting a huge amount of data because we just can't model, even in perturbation theory, a lot of the steps. And n-body simulations aren't totally reliable because of our inability to model baryons. So what ends up happening is that you cut very hard in K max, and you put a bunch of parameters that you hope model your physics accurately. Using this approach, we've produced two groups have produced the first constraints on FNL equilateral from large-scale structure last year. Previously, no one had ever been able to do it. These constraints are not competitive with Planck. They're a factor of 10 away. And this is a very challenging analysis. Now, forecasts exist in the literature that are all over the map. They make completely different assumptions and they come up with completely different answers. So all kinds of experiments propose that they're going to be able to measure equilateral. Their sensitivity is kind of unclear. Some of them look competitive, like they're getting down to the kind of threshold we're interested in, but they make different assumptions. Now, all of this confusion is because we really are just trying to model something we don't understand with a bunch of free parameters. The hope is that bringing back this idea of protected observables might save us. And so specifically, this equilateral non-Gaussian signal really can be traced to quantum mechanical fluctuations at the path intersection of the light cones of the 3 points we're considering. It's really fundamentally due to something in the distant past, and it can be shown to be completely non-local in space. Now, all of the late time nonlinearity is very local. Dark matter doesn't move very far. And so the nonlinear triangles you produce tend to be kind of clustered into groups because they're just local nonlinear evolution. Now, in practice, this doesn't show up when you project all of the late time nonlinearity onto a single triangle. But if you use all of the information in the map, you can separate these, at least preliminary estimates show that you can separate these two kinds of signals and may offer an opportunity to still pull this primordial signal out of the data. Okay, so let me summarize what I've talked about. So the core theoretical progress in inflation has really been about understanding correlators. The EFT of inflation has been really powerful in framing the kinds of questions we want to ask. Cosmological bootstrap is really pushing us forward in terms of what we can actually calculate analytically. The issue of loops is now, I think, a mostly understood problem, although there's still some loose threads to be understood. But really the problem is now technology. Everything looks a lot like flat space EFT field theory, but to actually calculate corrections at loop order require developing regulators that are under better control. There exists a lot of really interesting non-perturbative physics, as in the tail of the distributions, fluctuations of rare events, high endpoint functions that might hold some really interesting signal, and understanding that better is really the next frontier on the theory side. Observationally, progress is going to come both from CMB and large-scale structure. CMB is going to be the key for gravitational waves. That's really the only way we're going to measure it. Cross correlations of the CMB and large-scale structure are going to be important for local non-Gaussianity, but the ultimate future is going to depend on large-scale structure. For primordial features, this seems like a home run. We're kind of guaranteed to be able to do these analyses. They've already been demonstrated. But all the stuff we want to do with primordial non-Gaussianity, particularly equilateral type, is really going to depend on some theoretical progress. Okay, thank you.
Thank you very much. Now the session is open for questions and discussions. Also, yeah, from the question.
Can you hear me?
Yep.
Thank you for the nice talk. I want to understand more the axion monodromy situation. You mentioned some oscillation signal appear in the power spectrum.
Yep.
But, yeah, this is a bit different from the quasi-single field inflation. In the quasi-single field inflation, some other massive field produce such oscillation signal, but in this case, it's a single field inflation, right?
So in quasi-single field, the oscillation is in the 3-point function. Yeah. It's an oscillation as you change the shape of the triangle. So it doesn't break scale invariance necessarily. It's a scale invariant oscillation because it's a cosine of a ratio of 2 momenta.
Okay, so in this case,
here it breaks scale invariance. That's the key point. And the reason it breaks scale invariance is because you just have a wiggle in the power in the potential. The potential itself has a wiggle in it.
So what determines the oscillation frequency in that case?
So in the oscillation frequency is a combination of 2 scales. It's the rate of rolling of the inflaton, so it's f pi of the EFT of inflation. That's what sets phi dot. And then the axion decay constant of the would-be axion. So in this case, because the entire idea is that the axion is so for the original model, they wanted super Planckian field ranges with sub-Planckian f pi's. So this sets a logarithmic frequency that has to be sort of bigger than 1, typically like 60 or something like that. That corresponds, this is this scale. So this is the sort of logarithmic frequency. So those models of axion monodromy would be like right in the middle of this frequency range.
Mm-hmm. So do you think it's possible to, how to say, measure the decay constant in this observation?
If you measured R, absolutely. If you detected R and the oscillations, you would know the decay constant.
Okay, thank you.
Okay, so are there more questions?
Yes, thank you for the nice talk. I just have maybe a naive question because I don't know much about it, but I wanted to understand a bit better if you can tell us some words about it. What you meant by we have technology problems in calculating the loop corrections in the sitter, and what is the thing that really breaks down, for example, with dimensional regularization, you mentioned it, and maybe also with other kind of regulators that we know from flat space physics.
Okay, great question. I'm happy to talk about this. So, okay, so dim-reg fails because the way that we normally do the calculation, so time and space are different. So we often have to split time and space in our calculations. So the way that people normally split time and space breaks the entire idea that the integrals are scaleless. So what happens is you can show that in every dimension, you have infinity in every dimension. So it doesn't matter. You're like, usually what happens in dim-reg is that the naive divergence is different in different dimensions. So you pick up logs in the critical dimension, and then everything else is a power law divergence, which because the integrals are scaleless, just give you 0. Or give you a nice finite number. In de Sitter, you can see that the simplest thing you can show is just that all the integrals are infinity in every d for every mass. So the strategy that will probably work is Mellin space. Mellin space, you don't split time and space, and you have all these Mellin integration variables, and you get lots of things that look like dim-reg-like regulators. The problem is that understanding Mellin space regulation past one loop is just not very well controlled. So you get like these infinite series of poles that you have to integrate around. So it becomes this entire problem of choosing contours in a space where there's like, you have these expressions that are products of like 15 gamma functions, and you have to pick a contour that goes through this expression of all the poles of these 15 gamma functions and picks out the right answer. So that's a very technical answer, but the issue is that dim-reg doesn't work because the things aren't scaleless, and so you need to introduce these kind of less conventional regulators where just less is known about how to compute finite answers.
Thank you.
Okay, thank you. Can I ask a question?
Of course.
The inflation predictions normally sensitive to the period of reheating process. In particular, number wave folding, if the
in multi-field inflation.
And my question is whether there's some observational consequences from your perspective. I mean, observational consequences of reheating process from your perspective.
So I would say there are kind of multiple answers. So in single fields, the answer is no unless you produce gravitational waves. In multi-field inflation, so let me go back. So in multi-field inflation, the usual answer is that when the reheating process is local, like again, it's local in space. So typically you can think of it as some kind of expansion that's local in space. So there's the x here is the same x on all sides of the equation. So you'd expand this in local operators, and you'd say, okay, the density, all that reheating is going to do is express the precise coefficients of this Taylor expansion. Now, the reason I'm saying that that's not totally true is that there are models like the one I've tried to draw where there's a highly non-linear relationship, and it's not useful to Taylor expand it. So the opportunities where really interesting things can happen from reheating are the situations where what reheating does can't be reduced to the Taylor expansion of something simple, but that there's really nonlinear information related to reheating. So this is something that like Dick Bond and collaborators have been working on for a long time, and they often call this intermittent non-Gaussianity, and there they really do see that the physics of reheating shows up in some really non-trivial way in the statistics.
Okay, thank you for your comment. I don't know if there's some question also from Zoom or for the question from the auditorium. Otherwise, let's thank Daniel again for his wonderful talk.
Thank you so much.
Thank you very much. Yeah, we'll have a coffee break for 30 minutes, about 30 minutes. So we are coming back at 11 a.m.